Okay, so let's begin with the first presentation. This is integrated design, how to produce high performance and green buildings. So our key audiences for this presentation are, I know we're teaching at a university and many of you, if not most of you, are students, but our main focus for this morning's presentation is architects and engineers, construction managers, and energy service providers, people in the private sector, and we're trying to raise the technical capacity of these people in order to produce better buildings. It's primary audience. So the second audience is building owners, investors, developers, lenders, bankers. And the third audience is MOC, Ministry of Construction, Departments of Construction in the major cities and provinces, and public sector building owners and operators. And the objective here is to enable government officials and staff members to better support the delivery of high performance, low energy, green buildings in the public sector. Okay, so our topics are integrated design for high performance buildings, for green buildings, and even net zero buildings. So zero energy buildings are really good low energy buildings that you can add photovoltaics to. And with photovoltaics generating electricity in addition to low energy, the building over a year's time doesn't use any electricity from the electrical grid. Sometimes it uses electricity, other times it gives electricity back. In the state of California in the US, there's an objective that 15 years from now, in the year 2030, all new buildings will be required to be net zero. The federal government in the United States also has a similar objective. Okay, so now we're going to look at space loads, energy use, and greenhouse gas reductions. How many of you are architects, architecture students? How many? Most? How many are engineers? Most are 1 and 2 engineers. Ah, okay. 3. Okay. Mac, you're in low group. This is usually everybody's engineers. Okay. I think that the goal for young architects and engineers in Vietnam and everywhere is to learn how to design buildings that have virtually no negative impact on the environment, that the buildings are so efficient, the building form, the siding, the orientation, the use of windows, the use of overhangs, the careful use of ventilation, everything is designed to produce a comfortable, beautiful environment that has minimal impact on the environment. So the architect's goal is to produce a building that is beautiful, very comfortable, and has almost no impact on the environment that is negative. Yes? Yeah, low impact. And the idea of integrated design is that the architect, I'm an architect, Mac Wallace, an engineer, we work together so that if I produce a design that has minimum impact, I can say to the engineer, you can install a very, very small air conditioning system that doesn't need to be used all the time. And the other thing that you as architects need to learn to do is to not permit your engineers to use their standard, what's it called, rule of thumb, where they simply install so many tons per square meter of floor area. Can't do it anymore. The engineers can no longer use the old techniques of steady state analysis. They need to use dynamic analysis hour by hour for year time to do sizing. Okay, this is a big idea. Yi Chung Wong, I'm not sure I'm pronouncing that right. It's from National Geographic magazine. This concept shows the world as a bathtub, and it's filling up with water, and the water is actually greenhouse gas of CO2. And every year, 9.1 billion metric tons of CO2 is produced into the atmosphere, partly from human activities. Each year, the oceans and the plants and the trees and the forests are able to absorb only 5 billion metric tons. The other 4 billion metric tons stay in the atmosphere. So we're building up increasing CO2 in the atmosphere. This is one of the producers of global warming. what you will see in the next half hour or so is that the building stock, the building industry, the building stock in Vietnam is growing very rapidly. And over the next 20, 25 years, it's going to increase by 600 or 700%. With that growth, Vietnam will be contributing more and more to the CO2 in the atmosphere. So it is very important that your new buildings here in Vietnam are as efficient as possible and minimize the greenhouse gas production. So I've already said this. So here's a recent increase in electric power consumption. This is the use of electric power in Vietnam for industry, for buildings, for everything. And you can see that in the last 10 years, there's been a 400% increase in electric power consumption in the last 10 years alone. Okay. Now, here's just some growth rates of electricity use in the three major cities. 200% in Da Nang and 200% in Ho Chi Minh and 300% in Hanoi over the last 10 years. Okay. And this is really interesting. This shows that buildings, service and commercial buildings, public buildings and commercial buildings are using about 38% of all of the electricity used in Vietnam. Over half is used for industry and construction, but almost 40% is used by buildings. So over the next 2 days, we're going to show you different examples of how to start with current practice of construction of buildings and design in Vietnam and reduce the energy use. We're using offices, reduce the energy use 30% to 50%. And when you reduce the energy use, you reduce the greenhouse gas production. So if you're reducing energy by 30 to 50%, you're reducing greenhouse gas output by 30 to 50%. So this shows the amount of electricity used in the three major cities by buildings. And in Da Nang and Ho Chi Minh, it's 37 to 39% of the total electricity use is by buildings. But in Hanoi, over half of the electricity used in Hanoi is for service and commercial buildings. And that includes residential, so it's administrative and household as well. So this chart shows that residential apartments growth is quite rapid in the last 5 years and moving ahead into 2020. This is apartments and it's very high growth rate. And here this shows that in the last 10 years, apartments and offices have been the two building types that have grown most rapidly in square meters of floor area. And then, what did I do? Let me go back. I'm out of sync. Okay, let's go. Okay. This is a very interesting chart. A year and a half ago, when our project, our VCEP project started, nobody knew how many big buildings were constructed in Vietnam each year. Did not know. There were piles of paper, but no data in the computers, no way to know this data. So we took the challenge for the 5 biggest cities, Can Tho, Ho Chi Minh, Da Nang, Hai Phong, Hanoi. And we asked consulting groups in each of the 5 cities to collect data for the last 10 years. How many buildings, large buildings over 2,500 square meters have been built in the last 10 years? And so far, we have collected data for 3 of the 5 cities. We have Can Tho, Da Nang, Ho Chi Minh. We are now collecting data for Hanoi and Hai Phong. And what we're showing here is data for Ho Chi Minh on the left and Da Nang on the right. And I will talk about this in a minute. So we have for both cities, we have data for actually 20 years, but the data for the last 10 is better. And we see that in the last 10 years, there has been major growth in buildings in both Ho Chi Minh and Da Nang. And Da Nang, the growth is more recent, but very, very rapid. I can remember visiting Da Nang in 2003, my first time in Da Nang. It was a slow provincial city. Today, very, very active and tremendous growth. So we're seeing that Vietnam is growing very rapidly. So we're trying to teach you in the next 2 days and in the next year, we're trying to teach you how to know how to have all of the buildings in the next 10 years use half the energy of these buildings, half the energy. Okay. Now, with this data, and Mr. Fong, who is sitting in the side over here, is the manager of the data collection process. And he's become an expert in getting contracts signed through the Vietnamese system and the American system. Very complex. But what this data allows us to do is we can begin to, we can begin to think about policies and what the policy impacts will be on energy use. And this slide shows the current energy use in, what is it, millions of megawatt hours per year, or yes, millions of megawatt hours per year, and we're just under 2 million. And it's going to grow from 2 million to 11 million by the year 2040 in the next 25 years. So what we're looking at is, what if we improve the compliance with the existing energy code, and every 5 years revise the energy code so that it requires more efficient buildings. And if we do that 5 times, we will reduce the energy use this amount. Doesn't seem like much, but we can also do additional actions to improve the efficiency. And instead of having the building energy be this great in 25 years, we can have it be this great. So what we can do is work with the Ministry of Construction and the Departments of Construction to improve the efficiency of buildings over time. And this is the reduction. This is a reduction in tons of CO2 over 25 years. So the policies we're talking about with the energy code, or our program, can reduce greenhouse gas productions by 1.2 million tons in the 25th year. That's 1.2 million tons every year. And I think the accumulation of savings is in the order of 8 to 9 million tons over the 25 years. That's a lot of CO2 reduction. So to achieve these results, you need to learn how to design and construct more energy efficient green buildings. So this is the history of energy codes in the United States over the last 40 years. One more. And what we can see is that in the U.S., the energy code today in the U.S. requires buildings that are over 60% more efficient than they were 40 years ago. 60% more efficient. And in the last 15 years, the level of efficiency has improved much greater than it was earlier. And the code in the U.S. is developed every 3 years and changed every 3 years. So the energy code in the U.S. is developed by the professional societies, and then it's approved by the federal government. So Mac Wallace and I have each spent 12 to 15 years working on the energy codes here. So here's a chart that shows for the US the level of energy use in buildings, the average energy use in buildings in kilowatt hours per meter square in parentheses. These are kilowatt hours per meter square. And the building stock 10 years ago in the US was using 283 kilowatt hours per meter square of floor area as an average. Now, today, the energy code requires an energy level of 175 to 160 kilowatt hours per meter square, much less than the buildings of 10, 15 years ago. And each year, and the energy code is going to come up next year with the 2016 version, but the best practice in the US today is about 80,000 kilowatt hours per meter square. And at that level, you can add photovoltaics to produce a net zero building. Okay. And to achieve high performance buildings, a goal for the architects is to reduce the space loads 20 to 50%. The space loads mean that the loads on the air conditioning is reduced 20 to 50%, and the size of the air conditioning can be reduced that much too. So the way this tends to work in integrated design is that the cost of the glass for the windows, the cost for external shading, the cost for a better lighting system goes up a bit, but the cost of the air conditioning goes down because there's less load. So another way to state the goal is for architects to produce building architectural features that are as sustainable, resilient, and green as possible. Okay. Let's look at some energy patterns by building type. How is energy used by building type? And the building types we'll look at are Van Fong, office, hospital, education, residential, retail, and hotel. These are 6 of the building types. We're actually looking at 15 building types. These are very simple geometries, but they let us analyze these buildings in the computer very quickly, and we can examine the impacts of changing building features to make them more efficient and more green. Now, this is a really interesting chart because it shows the energy differences for 3 cities, Hanoi, Da Nang, Ho Chi Minh. And you see that the energy differences for an office building between the three cities are not very much. The energy differences for hospitals or for education or for apartments or for retail or hotel, there's not much difference from city to city. Not much different. But there is tremendous difference between an office, a hospital, an apartment, a retail store, one of your malls like Vincom, or a hotel. So this is really interesting information. And what we are doing in the project right now, and Fong is actively involved in managing this, we are now collecting data on about 225 large buildings throughout the country. We have 4 teams of contractors, 2 in Ho Chi Minh and 2 in Da Nang, collecting 75 to 100 buildings in each city. And we will be able to refine this data over the next year and have better information about current practice for energy use. I'll just keep going. Fong, do you want to comment on the? I think he missed what I was saying about what we will be collecting data that will let us refine this information for each of the building types. Yeah. No? What I'm saying is this data was collected by the World Bank 5 years ago. Our data that we're collecting now will give us much better data than this about each of the building types in the cities.
Khảo sát cách đây 5 năm thì bây giờ dự án của tôi đang thực hiện khảo sát chi tiết hơn rất là nhiều đối với khoảng 250 công trình ở 5 thành phố lớn, và cái công việc khảo sát này thì tôi đang thực hiện từ giờ đến khoảng tháng 3 năm 2016 sẽ xong, và sau khi xong thì chúng tôi sẽ có cái dữ liệu chính xác hơn rất nhiều.
Thank you. All right. Now this we get to more detail. We take 2 building types, the apartment and the office. Here's the office, Van Phong and Nha O, the residential. And we take it for 2 cities, Hanoi and Ho Chi Minh. And we see in each case, the apartment buildings use about half of the energy that the office use in each city. That's per square meter of floor area, half the energy for apartments. The other thing is there's a big difference in the way the buildings use energy. The office buildings, about half of the energy is for lighting, for elevators, and for fans to move air. The apartment buildings, on the other hand, use very little energy for lighting, fans, and elevators, very little, but the apartments use almost half of their energy for water heating. So the other thing we see is that office buildings use very little energy for heating water, whereas apartment buildings use a lot of energy for water. So what we don't show here is the pattern of energy use by month is very different in Hanoi and in Ho Chi Minh. In Ho Chi Minh, every month is about the same. In Hanoi, it goes very, very big usage in the summer for cooling, but not very much in the winter. And now we have variations in climate and climate data for Vietnam. And what we see is that Vietnam, all of Vietnam from north to south, has very similar weather when compared to the United States. The United States gets very cold in the north and hot and humid in the south. And for Vietnam, Vietnam weather is very similar to just the southern part of Florida. So one of the reasons that Mac Wallace as an engineer is so useful here in Vietnam is that he lives right here in Texas and he works here in Texas. And the climates here in Texas, especially around Houston, is extremely similar to the climates here in Vietnam. For much of the year, the temperature and humidity in Houston and in Hanoi is very similar. Okay, so here's the pattern from January to December in Hanoi, and you see that the temperatures rise in the summer and get lower in the winter. And here's the pattern for Da Nang. Similar pattern, a little hotter in the summer and more sunshine than Hanoi. Here's the pattern for Ho Chi Minh. Almost every month is the same, and the peak in Ho Chi Minh is March to May in the springtime, right here. Now, this is not an interesting slide, but it says that until recently, we only had detailed data for one city in Vietnam, and that's Hanoi. And we have on our project, we are using software to generate detailed data for every hour of the year, 8,760 hours, detailed data for all the weather variables for Ho Chi Minh, Con Tum, Da Nang. We haven't done Haiphong yet. Yeah? Okay. Okay. So we're also using a very good piece of software that is free to analyze the climate data. It's called the Climate Consultant. It was developed at the University of California in Los Angeles. And Los Angeles has perhaps 1 million Vietnamese living there at this point. Very large population in LA. But the UCLA has developed the Climate Consultant. It's free. You can download it from here. And Vu is going to present a series of slides that show output from Climate Consultant for analyzing the climate in Hanoi. Okay, so we're now going to start the next presentation. Vu, I'll turn this over